Welcome to the Triple Physics Paper 2 Sound and Vision presentation. When waves hit different objects or different boundaries between objects, one of three things can happen to them. They can be reflected at that boundary, bouncing off. They can be transmitted, pass through that boundary. Or they can be absorbed, soaked up at that boundary, and the energy does not pass on. When a wave is reflected at a boundary, then the wave hits the boundary and bounces off at the same angle. We say that the angle of incidence, labelled I on the diagram, is equal to the angle of reflection, marked R on the diagram. We're used to drawing that with straight rays of light for mirrors, but don't forget it's also true for any waves that hit an object as well. The wave front will reflect at the same angle. Two different sorts of reflection. When waves reflect off a smooth surface, all the waves are reflected at the same angle of reflection. But when they're reflected off a rough surface, they're all reflected at different angles. When a wave passes through a boundary from one material to another, if the materials are different densities, then the wave will change speed and refract. The example we're most used to is a ray of light passing through a glass block. The wave hits the boundary and changes direction. It refracts. And then it crosses another boundary and refracts again. When we're measuring how much the wave changes direction, we look at the angle of incidence again, and then the angle of refraction. When the wave changes speed, that's what causes the wave to change direction. When a wave goes into something denser, for example, going from air into glass, then it's going to slow down. When it goes into a less dense medium, it's going to speed up and go faster. So we say that when the ray goes from air into glass, it refracts towards, it bends in towards the normal. It does the opposite on the way out. It bends away from the normal. And we remember this with our tagaga. Towards the normal when you go from air into glass. Away from the normal when you go from glass into air. Now, you might have to draw the wave front version of this diagram. Remember, a wave doesn't just come in as a straight ray of light in real life. It actually comes in as a series of waves. If you want to show waves speeding up, then make sure you draw your wavefronts closer together as they've gone through. If you want to show it slowing down, draw them further. Lenses are used to refract light to form a nice clear image. Two sorts of lenses: convex lens, which curve outwards, and concave lens, which curve inwards. A convex lens, parallel rays of light which pass through a convex lens, all get refracted inwards and end up being focused at a focal point, the principal focus in front of the lens. The distance from the lens to the principal focus is called the focal length. You can measure that in meters. The symbol for a convex lens shows how the lens curves outwards. A concave lens refracts rays of light outwards as they pass through the lens. They are all refracted as if they had come from a point behind the lens. So they are refracted as if they had come from the principal focus. That means when I measure the distance from the principal focus to the lens, it's a negative or minus number. The symbol for your concave lens shows how the lens curves inwards. When an image is formed by a lens, it'll be a different size to the object. When you work out the magnification, you just divide the height of the image by the height of the original object. It just comes out as a number, so it doesn't have any units, but do make sure that you measure the height of the image and the height of the object in the same units. So centimeters divided by centimeters, or meters divided by meters, and so on. You'll need to be able to draw a ray diagram to show how the rays of light pass through a lens to form an image. I'll attach the instruction sheet to the VLE. But in summary, when you make the image, it could be a real image made when real rays of light meet to form an image which you can project on a screen, or they could be virtual, made from rays of light which appear to come from a certain point, and those images cannot be projected on a screen. If you make an image with a concave lens, the rays of light going through the lens are never going to meet up, so you're always going to get a virtual image. Convex lenses can make real or virtual images. Here are the 4 steps for drawing your ray diagram. They'll be on the worksheet with the VLE. But basically, you always start off drawing in the object, which we're going to make an image of, the lens, and the principal focus, and the axis at 90 degrees to the lens. We just draw 2 rays of light. First ray of light is parallel to the axis, and it gets refracted down through the principal focus. The second ray of light goes straight through the center of the lens and does not refract. If the rays of light meet, that's where you've formed your image. If the rays of light do not meet, track your rays of light backwards to make a virtual image. Draw virtual rays of light. Sound waves can travel through solids. That makes vibrations in the solid. So although we're used to thinking of sound waves traveling through the air, they can also travel through. You need to know how sound waves in the air can then be transmitted through your ears so you can hear those sounds. The sound waves will travel down into your ear, and the first part of your ear they will reach is your eardrum. The vibrations in the air cause the eardrum to vibrate, and those vibrations are passed on through 3 tiny bones in your ear called the ossicles. That passes the vibrations on to this spiral, snail-shaped structure inside your ear called the cochlea. Inside the cochlea, those vibrations are changed into electrical impulses which can be sent down the nerve to our brain, which makes sense of the noise. So we're making the eardrum vibrate, vibrations passed on through the tiny ossicle bones, and the vibrations in the cochlea sending signals along the nerve to our brain. We do have to remember that those vibrations of sound waves will only cause vibrations in solids over a certain range of frequencies. That's why we can't hear any sounds lower than a frequency of 20 hertz or higher than a sound of 20,000 hertz or 20 kilohertz. Sound waves higher than 20,000 hertz, which we can't hear, are called ultrasound. And although we can't hear them, they still work the same way as any other waves. They can be reflected, absorbed, and transmitted, and they'll speed up and slow down in different materials. We can measure how these waves travel through different objects, and that lets us see inside objects that we wouldn't normally be able to. For example, boats can use ultrasound waves to work at the depth of water beneath them. The ship will send out an ultrasound signal through the water, which will then be reflected off the bottom, and the echo will be picked up by the ship. By timing that echo, we can work out the distance it's traveled, the speed of the waves multiplied by the time it took to come back. But be careful. If you've worked out that distance, that's the distance from the ship to the bottom of the sea and back again. So to work out the depth of the sea, you'll need to divide your answer by 2. We can also use this idea of timing the reflections in ultrasound scans of babies before they're born. A little ultrasound transmitter sends ultrasound waves inside the mother's body, and at each boundary it meets, so for example where it hits the skin, where it hits the fat layer, the muscle layer, the first layer of baby skin, bones inside the baby, at each boundary some of the ultrasound wave is reflected and some of it continues on. We say it is partially reflected at a boundary. Partial reflection at a boundary, or PRAB. When you're explaining how it works, explain that the ultrasound wave is partially reflected at each boundary and the echoes are timed to see the distance to each boundary. We can use that to look inside objects like blocks of metal, airplane wings, and other solids where there might be cracks or damages. If we time the reflections of ultrasound waves passing through objects, then we can work out the distance to each boundary. Our speed, distance, time sum always gives us that answer, but we must divide the distance by 2. Partial reflection at a boundary, or PRAB. Each boundary will give us a reflection. The waves caused by earthquakes traveling through the earth can also help us see what is inside the earth. There are 2 different sorts of waves made by earthquakes: longitudinal P waves and transverse S waves. If it helps you remember, the transverse S waves make the shape of a letter S. So S waves are transverse. So when an earthquake at one part of the earth makes those waves, they travel through the earth. But the different waves travel in different ways. P waves can travel through all the different parts of the earth, but they will speed up and slow down as they travel through the different solids and liquids. S waves cannot travel through liquids. So they've helped us to understand that part of the earth, which the S waves cannot travel through, are made from liquid. And the P waves have helped us understand which part of the earth are made from liquids, which part are made from solids, and how much the waves have slowed down or increased in speed, traveling through different materials.